So in the last lecture, we were here and we discussed the minute details about the support vector machine, like what they are and why this particular algorithm is called as support vector, because as you can see here, because of these points, if you see here, they are actually the support vectors and they help you in finding the decision plane. So as you can see from the equation also, this equation where you can see that for all the values of lambda j, see the lambda j star is actually coming from the algorithm that we are trying to solve. So here if you see, this optimization framework which we have discussed when we transform the space to dual. So whatever solution that you will get for solving this particular optimization objective is lambda star. So once you get this lambda star, based on the decision whether that lambda star is greater than 0 or equal to 0, you will decide the corresponding support vectors. So if lambda is coming out to be 0, that means they corresponds to the properly clustered points. So let me show you that. So if lambda is equal to 0 means all the points are correctly clustered and they are correctly classified by the support vector machine. But if your lambda comes out to be greater than 0 means they are the points which actually define this decision boundary, which is over here. And based on this decision boundary, you can actually find out this boundary, which is the center one, which actually classifies the two data sets. So this is actually lambda greater than 0 will actually select the data points which will give you the margin, that gamma margin. Right now here it is 1 because we normalized it. If you recall our earlier decision, we normalized it by gamma, so that's why its value is 1 right now. So so these support vectors actually help you in finding out the maximum margin for the problem. Okay, and this is what we wanted when we discussed perceptron. At that time we saw that perceptron was trying to find out the margin, find out the decision boundary, but it was not caring about the margin. So it can, you know, come to some specific data point, and I showed you last time that if that data point is slightly moving this side, then the whole algorithm will create problems. So that margin motivation which came from perceptron motivated the researchers to start with support vector machine. So this is the idea behind support vector machine, which tries to maximize the margin. So let's go further today and see what else we can have here. So this is nothing but it's basically what we are doing here is we are defining a set W, which is nothing but we are actually counting out j's. What is j? J are the number of, you know, x to the power x to the superscript j. You already know what this is. J is actually 1 to m. So we are trying to find out which sample has lambda star j greater than 0. So what we are doing is we are actually finding out the support vectors and we are putting it in capital W, just creating a set of that. And now you realize the optimal weights theta star is nothing but lambda j star, which you are getting from the solution of the optimization framework, which I have shown you 2-3 slides back, and then you put it over here and you find the solution. So it is nothing but lambda 1 x1 y1 plus lambda 2 x2 y2. Like this it will be up to lambda m xm ym. So wherever you have lambda values, that will be there in the summation, and wherever you have lambda equal to 0, they will obviously vanish off because most of them will be 0. Only few of them will be 1. So that is the advantage of this summation. So you see now, instead of having summation of j running from 1 to m, we are actually running up to the set W, which actually contains all the non-zero elements having lambda greater than 0, and that will be only 2 or 3 or 4 or 5. If you consider the whole data set, that data set is around 1000 samples, and out of that 1000 samples, only 3, 4 or 5 will be your support vectors. So you can see now how your summation actually reduces to only 4, 5 values. Rather than going for 1 to 1000, you are summing them up, you are only using 4 or 5 samples to form the decision boundary. So this theta star is nothing but it's a decision boundary which actually separates the two classes. So this is basically that. Okay. So the optimal separating hyperplane depends upon the support vectors. points closest to the decision boundary. It is different from the least square solution on the training data set. This one I have already discussed last time, that why it is different from least square solution, because least square solution will create problems because of this point. If it moves a bit, your boundary will change. Whereas in case of support vectors, if your support vectors position is not changing, then the decision boundary will remain fixed. So that is the advantage. Okay, so now the important thing is, once you have selected theta star, the problem is that you know the decision boundary is nothing but it's theta x plus theta 0, if you remember. Theta basically this, because we have separated theta 0, it's a bias term. So if you remember, we also have theta 0. This theta we have calculated, theta star x rather, we have calculated in the previous equation here. We have already calculated. The only thing that is required is theta 0, which is the bias term. So that is easy to calculate. What we can do is, we actually pick any support vectors x plus. We are calling support vector x plus because we are picking up a support vector in the positive class. So that's why I'm calling it as x plus. And then again we will pick one more support vector, which is x minus. So we are actually taking that support vector from the negative class. So can you tell me how we will pick these support vectors, on what decisions we can do that? Like if I want to pick the support vectors from the data set, can you tell me on what basis I will do that? Based on what uh, uh, decisions, like based on what variable we can say this is a support vector and this is not a support vector? Anyone?
Lambda.
Yes, good. So based on lambda, actually, it is deciding whether this particular point is on the support vector or it's not. So once we select these support vectors based on the value of lambda, what you can do is you can actually put this into the equation of the hyperplane. So this equation here is nothing but this equation, this one. So what we are doing is we are actually putting the x plus on this equation, and we are putting x minus on this equation. So if you put x plus on this equation, obviously it will satisfy the equation of the line, which is this one. And if you put x minus on this, it will satisfy the equation of the line, which is this one. So what we are doing next is, we are actually putting these values here. So in the x plus, if I put, I will get this equation. In x minus, if I put, I will get this equation. So once you solve these two equations, you can get the value of the bias term theta 0 star, and the value is this. So this is the equation of the hyperplane which we have got. That is, we got theta star, and what we are now having is theta 0 also star with us. So once we have these two, you know that you already know the equation of the hyperplane, because already the optimal values of theta star and theta 0 star is known to us now. So from these equations we can get that. So this was related to the dual setting, where we moved to dual space, and we saw that kernels, once we moved to dual space, we got to know the story of support vectors, because before that, when we were actually solving the support vector machine in primal space, we were not able to get this intuition whether what is support vector and why we are calling it as support vector machine. So based on this first transformation to dual space, we got to know that this is the support vector because of the story which I have told you till now. And the second advantage of going from primal space to dual space is it enables kernel trick. So this one I have already explained you in my previous lectures, that what this kernel trick is all about. So let us see how this enables kernel trick actually once you move from primal to dual space. So this is the optimizations framework which we have already discussed, that how we derived it, and the solution of this is actually lambda star, which you use for forming the support vectors, and which will be used for your definition of the hyperplane. So basically this is for your, as an exercise, you have to convert this into this format, where you can see you can represent this complete equation, which is double summation and all this stuff, into a matrix vector product, which is like this. So this is for you as an exercise. So try yourself, may or may not come in exam, so this is for you to do an exercise on it. So you have to convert this particular optimization framework, which is on the top, into a matrix vector product, which is on the bottom. Okay. So here, if you convert this particular optimization framework into this particular format, so if I look into this specific value of P, then what this P is? This P is nothing but it's a matrix which looks like this. So this, once you do this as an exercise by yourself, you will find that the matrix P will become this. So in this matrix, what you will observe is that there is, a dot product between the vector x1 with x1 itself. So if you see this particular thing, you will recall the story of kernel trick, where we were trying to do similar things. So here, if you observe this clearly, then what you will see is we have this dot product, and this dot product can be used to fuse kernel trick here. So last time also we saw how we were using kernel trick for dot products. So what we will do is, once we see this matrix P, what we can do is we can actually transform this into phi xi transpose phi xi. So phi is basically the transformation of the vector in higher dimensions, and from there you can write this as a kernel k xi xj. So this I have already covered in depth in our classification setting. So in case if you have any doubts, you can watch that lectures, but the motivation is coming from there. So in classification we used kernel regression. Here also we are using the same story, because we saw that there is a dot product between the elements. So let's use kernel and see whether we can gain some advantage by using kernels or not. So that is what we are trying to actually replace this particular product by kernels. So once you do this kernel setting, what happens is the SVM, which was linear SVM, when we started out with, it becomes kernel SVM. Why it is kernel SVM? Because now you are incorporating kernel into the optimization framework, so it becomes kernel SVM rather than linear SVM. So if you try to use kernel now, then can you tell me what advantages you will get? Like earlier we had simple things, right? We had xi transpose xi, but now if I try to use kernel here, then what advantages we will have? Any idea? Huh? No, faster is okay. That is one of the advantage that we had last time. That is okay. But what advantage you will get in terms of the decision boundary? Like what kind of decision boundary can you expect when you use kernels? Not studied kernels? So kernels actually try to impose non-linear boundaries, right? Why we were moving to kernels? We were trying to move to kernels because we do not want linear separating hyperplanes. We wanted non-linear boundaries to separate the data set. If you recall, we tried to increase the feature space by multiplying it by x square, x cube, right? So why that was done? It was done to create non-linear decision boundaries. So kernel SVM actually, or maybe anything which is related to kernels, actually tries to incorporate non-linear decision boundaries. So that's why we are using kernel SVM here. And the thing is, so now xi transpose xi is replaced by kernels. So we have done this over here. You can see the colors of, I'm representing it by purple here. So this is basically removing xi transpose xi with the corresponding kernel, which actually takes into consideration the sample with the sample itself. So the important point is, if you have something like this, if you have a data set which looks like this, if you see inside you have blue points and on outside you have green points. So you can see here, if you want to classify it through linear SVM, can it be possible to do that? Because you need a straight line, right, to separate this. But it's not possible here because it's a, first of all, something non-linear is required here, right? And the important thing is, here it is non-linear as well as it is separable. If you see the linear separable means what? Linear separable means you have some data, but it is separable. So this type of situation is linearly separable. What is nonlinear separable? Nonlinear separable is like this, which is shown over here. You can see you can separate the two classes, but you know that it has to be done through nonlinear decision boundary. You cannot use linear boundary here. That's why kernel SVM will help you out here, because it cannot be done by linear SVM. So the linear SVM that we discussed will not help you out. You have to impose kernels here, the RBF kernels which we discussed last time. So that will help you to create this nonlinear decision boundary, and this type of data set is nonlinear separable. Nonlinear and separables. And nonlinear non-separable will be what? It will be like this. Suppose you have, you know, like this. So it's like, you know, you cannot, it will be difficult to separate it, right? So it's nonlinear, non-separable type of thing. But this one is nonlinear and separable. So here we will use kernel SVM in hard SVM setting. So if you recall, we are calling the SVM as hard SVM. So this is basically hard SVM, and hard SVM, you recall last time also why we were calling it as hard SVM, because the boundary was fixed to 1. If you see the gamma, we divided by the thing, right? So that value is 1, so that is hard SVM. That is, the margin is fixed to 1. That's why it's hard SVM. Okay. So hard SVM along with kernels. So hard SVM along with kernels will enable non-linearity into a decision boundary, and you can use that one to solve these type of problems which is here. Okay. So this is basically the thing. Okay, so now if you see here, because the important thing here is this situation is okay. Like if you have this type of decision, or if you have this type of data set, you know that its boundary is non-linear. So what you can do is, if you are forced to use SVM, then you can use hard SVM plus kernel based. So the decision boundary will be a non-linear and can be separated. But now suppose you have something like this. Here you see we have we have this data set. You can see you have blue data set and you have some red data set this side. And if I ask you that you have to, you know, separate this particular data set which is given over here using Perceptron and using hard SVM. So if you try to use either Perceptron algorithm or you use hard SVM algorithm, so what your algorithm will, you know, result is, it will give you this decision boundary. And you can see that both these algorithms, hard SVM as well as Perceptron algorithm, will give you the same decision boundary. So we will show you also later on, once we finish this class off, we will show you that both the solutions are same. We will try to show you that. That is the solution which you are getting from Perceptron and the solution that you are getting from hard SVM. They are same but with minor changes. We will see that. But what can you say about this decision boundary? Is it a good decision boundary to separate the two classes? Why it is not a good decision boundary? No, it's
The
not.
margin is not maximized.
Yes. So the problem with this decision boundary is that points are very close to this decision boundary. So in case if some noise happens to come up, then it will, you know, jump this side. So it can be that type of situation where, so this is not a good fit. And even if you see in case of hard SVM, it is trying to maximize the margin between the two classes at his own, you know, it is trying best, but it cannot separate the two with larger margin, because you can see the points are very close. So it has a very small margin when you have hard SVM case. Okay. So what can be the solution? If you are the person who wants to separate these two data sets which are given over here, what will be your view? Like, if you are allowed to make some mistakes, what can you think of, like, which is the better decision boundary compared to the one which we have discussed here, the left? Like if I say that, okay, we can allow or tolerate some errors, then what will be the best decision boundary instead of this one? On the right one, this one will be the best decision boundary or not? If we allow errors, which errors This is the error, right? Because it's a red point, but it's on the blue side. So we are actually allowing errors. We are saying, okay, let's allow some errors. Let's not focus on too much on separating the two with all the points correctly classified. We are not, bothering about it. We are saying, okay, let's allow some errors to, come into the picture, and let's see whether we can get a better decision boundary or not. So if you see this boundary here, what do you think? Like, if I use this boundary, it has maximum margin also, and it is allowing some errors also within the margin. Is it right? So this is okay, right? This we can do, right? Like, we can allow some errors along with, but what we are gaining here, if we allow errors, we are gaining maximum margin. Still we are getting good margin here if we take this particular separating hyperplane. So this type of situation where you allow errors into the margin is basically called as soft SVM. So earlier was hard SVM, and in hard SVM what happens is you are not allowing any errors to lie inside this. If you recall, no data point was allowed to lie inside this margin space. But in case of soft SVM, you are saying, okay, let's allow some errors to move into the margin. And but the advantage we should get is the boundary should have maximum margin from both the sides, and it should be better as compared to the results that you are getting here. So that's why the idea of soft SVM comes into play here, by allowing errors into the margin. And if you try to use kernels here, then it will become kernel soft SVM. Earlier was kernel hard SVM, now it's kernel soft SVM. So this is the story behind hard SVM and soft SVM. So let us move forward and see how we can understand this soft SVM in more details. So here you see, I have shown you a diagram where what I am trying to show you is that we have these points which are labeled as A, B, C and D. So if you see the points A, B, C and D, these points, what is happening is, just a minute. So if you focus on A, B, C and D, what you see is that point A and point C and point B, they have crosses. Are you seeing it or not? We have crosses here, right? These points, these are crosses, right? So the two crosses are on wrong side because we have the data set consisting of cross and zero. So we have data set consisting of cross and zero. We want to separate crosses from zeros. And you can see from this particular data set that point A, point B and point C, the three crosses are appearing on the wrong side. It actually has to be on the other side, like it has to be this side, right? But it is on the wrong side. So A and C is completely on the wrong side. A is completely on the wrong side, but B and C are actually inside the margin, which we are saying, okay, let's allow that errors to percolate. So we are saying B and C are the errors inside the margin. A is the error which is completely off the margin, it is on the wrong side. And D is again 0, which is in the zero, which is in the X data set, and it's also completely off. So what we want to know is, we want to see whether we can quantify these results. So what we will do is, actually we will try to see, if I put this point into this equation, it will give you a value of negative more than -1. So because this is actually, whatever value you will put in this line, it will give you value of negative value, like let us say -3, -4, -5, because this boundary is -1, right? So all the equations which are below this will have more negative value. It will be -2, -3, -4. So it can be anything. So if I put this point A into this equation, which is over here, so what we will get is, we will get this equation. And let us say the value which comes out by putting point A into the equation of the hyperplane, we get, let us say, -0.15. Let us say, I'm just cooking it up. So if you see here, this point is on this side, so it will be more negative only. So let us say at this point, once you put it into the equation, you will get minus 1.5. And if you put this point, the point C, into the equation, what you will get is you will get a value in between 0 and minus 1. It will be, let us say, 0.5, minus 0.5. So because you can see one range is 0, another is minus 1. So whatever value that, whatever points you will put in between, the value will be minus 0.5, let us say. And in this case, if you put the equation, it will give you plus 0.5, let us say, because it is between 0 and 1. And if you put this equation, this point into the equation, it will give you, let us say, 2.5. Let us say, I'm just cooking up the things. So this is very easy. It comes from coordinate geometry. You put the points, and if you will get more value, right? Because this side is much higher than 1, and this side is less than 1. So anything, and this is basically in between minus 1 to 1. So whatever value you will put, you will get somewhere in that value range. So what I am doing here is, for the point A, if I put that point A, I will get, let us say, minus 1.5, and I am rewriting it as 1 minus 2.5. Same thing, right? Whether I put 1 minus 2.5 is minus 1.5 only, right? So similarly for point B, if you can recall from the earlier slide, what we are saying is, let us say it's 0.5, and I can write it as 1 minus 0.5, so it's the same thing. Similarly for point C, it will be minus 0.5, and we can write it as 1 minus 1.5. Same thing, right? So just some tricks. So if I call this value 2.5 as zeta, let us say, so all these values which are over here is zeta 1, zeta 2, and this one will be zeta 3, and for the last point it can be plus 1.5. So what we can do is, we can write it as 1 minus 2.5, because it's the same thing. Please note, these labels have to be kept accordingly. So in this particular case, since you are actually using the D point, this D point, the label for this 0 is actually minus 1. So what we are doing is, we are actually putting minus 1 here. So once you do that, this is again zeta 4. So what if you observe this particular scenario, what you will see is there is something like 1 minus zeta. Everywhere it is 1 minus zeta for the wrong classified samples. So if you see here, all these samples which are I have pointed out, you will have a pattern of 1 minus zeta. Whereas for other samples which are properly classified, we take zeta as 0. But for others which are wrongly classified, we can see from the calculation which we have done, it is 1 minus zeta. So this is all 1 minus zeta. So now what is actually zeta? Zeta is nothing but it's a distance of the wrongly classified point from the correct hyperplane. So for example, this point X, its zeta is how much? Its zeta is 2.5. Its zeta is 2.5. So what it means is, what I am saying is, wrongly classified points distance from the correct hyperplane. So correct hyperplane is this hyperplane for this point. So if this X is here, then it's correct, right? Agar ye X idhar hoga, then it will be a fine, right? It will be fine. So this is the actual correct hyperplane for deciding whether this X is right or not. So zeta is actually telling you that if it's a wrongly classified point, then how much distance it is from the correct separating hyperplane. So for X, the correct separating hyperplane is this one. So its value is 2.5. Similarly, if you do for the others, like for this particular case, if you see here, or maybe you can see this one, again this value is 2.5. Why? Because this is a wrongly classified point, but the distance of this point from the correct hyperplane is 2.5. So this is the correct hyperplane for 0. So that's why zeta is actually telling you that distance. So if you formulate the optimization framework again, in case of hard SVM, you remember the constraint was this, greater than 1. But now when you are using soft SVM, the constraint becomes this. And I hope now you must be knowing why this zeta is coming, because I have told you from the derivation how this zeta is coming from the diagram. So the constraint is, instead of using 1, which is the hard SVM case, now you are actually relaxing the boundary, and this is the soft SVM. So if you do this, what happens is you are actually allowing errors to um, move into the boundaries, within the boundaries. So so this is basically the 1 minus zeta, which is trying to relax the boundary for the SVM. Earlier the boundary was hard SVM. Okay. So if you remember the hard SVM case, in the hard SVM case, we had this one and we had this boundary with 1 only. But now in case of soft SVM, things are changed. What we are doing now, we are adding an extra parameter C xi square. So this is L2 norm. If you recall our cases of regression, where we were doing regularization, so we are trying to use L2 norm of this zeta parameter, and this is the regularization parameter C. Earlier it was lambda, if you recall. Now it is C here in case of SVM. So this is the optimization framework, and you are trying to minimize xi, because you want to minimize xi, right? If you minimize xi, then the points will be correctly classified. And this is constrained to this equation. Now earlier this was not there, but now it is there in case of soft SVM. So this is the framework for soft SVM. And another constraint is that your xi should be, zeta should be greater than 0, because if it is equal to 0 means it is properly classified, and these two constraints will actually set up the optimization framework for soft SVM. Okay, so now if you see this diagram is pretty intuitive. Here what we are doing is we are actually increasing the regularization parameter C. So C is the regularization parameter. So if you increase C here, I told you last time in case of regularizations of linear regression also, that if you increase lambda, the corresponding thetas of the separating hyperplane will get close to 0. I told you last time, if you recall our earlier lectures, if you increase lambda and you are trying to minimize the objective function, then the corresponding theta of the hyperplane will go close to 0, underfitting and overfitting, if you recall the lecture. So here same story is going. If you increase C, your zeta will become close to 0, as pretty obvious, in the same way as it was in case of linear regressions when we were discussing regularization. So what we are doing is we are making zeta going close to 0. That means the classifier has a tendency to make mistake on training data decreases. So basically when your zeta becomes close to 0, it will try to classify all the data points properly. So somewhere or the other, it is actually acting as an overfitting. So you are trying to fit every data point in the data set, which is not advisable. I have told you in our earlier lectures also the problem of overfitting. So it is trying to do that same story here by correctly classifying all the data points. Whereas if you decrease C, what will happen? Your sigma will increase. It's obvious, other way around. So what it is trying to do is its tendency to allow mistakes to enter into the margin increases. So basically, if you increase zeta as high as possible, more points will enter into the margin. So it is a situation of underfit. So you are actually, you can say, bias. So the classifier has a high bias because it's creating errors in most of the data sets. So you can see on the bottom part, there is a comparative analysis on the way you tune C. So if this is the case of hard SVM, which you already know that no data points are allowed inside the margin, no data points are allowed here. So this is the case of hard SVM. If you keep large C, you can see here your zeta is close to 0. If you keep very large C, that means the results that you will get in case of soft SVM, even if you increase C to a very large value, what will happen is it is equivalent to hard SVM. Both the answers will be same. They both will match. Whereas if you keep medium C, what will happen? In that medium C, you will allow some errors to move inside the margin when you keep medium C, because in medium C you will have some sigma value. If you use very small c, more sigma value will become more high, and or large number of data points will come inside. And the important point that you will observe is that this margin is increasing. Earlier case here, if you have a margin, let us say x, and this is x2, then x2 is greater than x1. As you increase sigma, your margin is also changing as per the things. So this is basically showing you the pictorial representation, and you can see how soft SVM variation. So the soft SVM has three variations: small c, medium c, and large c. How they are, how large c converges to hard SVM. So this is actually trying to show you that story. So this is basically another variant of your soft SVM. In the earlier case, I used L2 norm here. But now I am using L1 norm this side. So L1 norm is equivalent to lasso regression, which we had discussed last time. So same story here. So whatever advantages you got from lasso regression, the same advantages you will get here in case of this SVM. So what will be the advantage? Advantage will be that this sigma will be sparse and only few samples will be allowed to live inside the margin. So basically whatever errors that you are trying to incur by putting them inside the margin, that values will be small because lasso supports sparse data. So that's why very few samples of unclassified points will be inside the tube, or you can say the margin. So this is the advantage of using L1 norm in the case of SVM. Okay, so this slide tries to link Perceptron from where we started out, and we saw that Perceptron has some problems and why we moved to SVM. So it is trying to show you a link in between the two, that are they same or are they different? So let us try to see that. So in case of soft margin SVM, I told you already that that zeta is greater than 0, and this constraint is already there. So basically what we are trying to do is we are trying to satisfy both the constraints, this one as well as this one. So we are trying to actually satisfy both these constraints. So if I want to satisfy both these constraints, we can actually write this. So this equation actually satisfies both the constraints. What it is trying to show you is that either it will be 0, because max of 0 or some value. So either it will be 0 or it will have some value, this one. So it is if you write this equation, this is equivalent to writing these two separate conditions, that is zeta greater than 0 and zeta greater than 1 minus this. So if you want to incorporate both of them, you can actually use max operator, which will try to consider both these conditions together in single equation. So now if you recall, this is basically the L1 norm of the soft SVM. This is what we have done last time, right? So this is L1 norm, and what we are doing now is we are just substituting this value with this value, and this is what? This is the same as this one. So what I am doing, I am just putting this value, which is equal to this, into this equation here, just substituting the value of zeta. Okay. So if I substitute this value, then the loss function for the soft SVM becomes this. So this is the loss function, and the corresponding training loss, which you will use for training the soft SVM, the loss will become this. This is the loss. So what we are doing here is actually, I am actually dividing with both the sides by C. So if I divide by C, here it will be 1 by C, and 1 by C I am calling it as lambda. And recall that this lambda is equal to 1 by C. Okay. So this just simple manipulation. So your training loss is this now. Earlier your training loss was different. So now what is happening? What we want to know is this particular expression. We want to understand what this is. If you recall the perceptron loss, in the perceptron loss, this one was not there. It was not there. But in case of soft SVM, this one is also there, as well as this theta is also there along with that. So in perceptron loss, recall that you only had max of 0 minus this. Okay. So this is basically trying to show you the max 0 minus something and max 0 comma 1 minus something. So this you know is coming from soft SVM. This you know is coming from perceptron, right? So what we are trying to show you is the loss function for this max. So here you can see this particular thing is the correct decision boundary and this is the wrong decision boundary. Can anyone tell me why I am calling this side as correct decision and why I am calling the left side as wrong decision? Anyone? Positive class. So, like, can you go more into why this particular thing is correct decision? Positive means what? Okay. On which conditions it will be positive? When theta will be and yi, what will be yi? Then only it will be positive, right? So same thing is going on here. So if your yi as well as this, if both of them are positive, that means what? You are actually trying to say that the decision which is coming from the decision boundary is positive as well as label is also positive. So multiplication of both of them are positive. So that's why this is correct decision. Whereas if this comes out to be less than 0 and if your label also is also less than 0, then multiplication of that will be again positive. So that's why this boundary is correct decision. And the left side is wrong decision. Okay. So what you can see from this max curve which is given over here, by seeing the curve, what you observe is if you are making correct decision, there will be no loss. Obviously, because if the decision is correct, what is the point of making loss, like loss function high? Why to penalize? So we do not want to penalize, right? So this is basically showing you that. Whereas if you make some wrong decisions, you will be penalized hard by this particular curve. Okay. Same thing is on the right side, but the only difference is now the vertex is at 1. So here the important point is that even this is basically the correct decisions. What happens is this particular region where also you have correct decisions, you will still have some loss. This is already there. But the important point to take care is that in correct decision also you are making some losses. So we want to see what kind of points in the SVM are there which actually creates this problem, that is even you make correct decision, you have some losses. So let us try to see that. So here if you see all the data points which are here, this one, you can see the labels of this are all +1 as well as they are greater than this, right? It will be giving you a value greater than 1. So multiplying both of them will be positive. Similarly, for all these points here, also you will have the opposite case, same case, because yi is negative as well as the decision coming out from the hyperplane is also negative. So multiplying both of them will be positive. So you will be having all these points which are circled here and circled there lying in this region because it's a correct decision. Whereas if you see these points, this point and this point, what is the problem? The problem is in this the label is minus and it is lying on the positive side of the hyperplane. So your theta transpose x plus theta 0, this value will be greater than 0, but this value is negative. So multiplying both of them will be a wrong decision. So that's why uh, uh, this point which is over here, you can see the blue line which is going over here. So this is the loss which will be incurred because of the wrong decision. Similarly, this plus point will have the label plus 1, but the decision boundary theta transpose x plus theta 0 will be negative. So multiplying both of them is again a wrong decision. So it will give you this loss. Okay. What about these 2 points? In these 2 points, if you see, they are correctly classified because this is the separating hyperplane, right? So this is a proper hyperplane, which and plus is on this side, minus is on this side. So they are actually correctly classified. But what happens here is this plus and this minus, though they are correctly classified, but their corresponding labels are creating problems. So that's why these particular, though they are correctly classified, they will be lying over here. They will get this much amount of loss because you see here the value of the hyperplane is between 0 and 0.5. This value, the value of this point will be between 0 and 0.5. So you are somewhere in between 0 and 1. So you are somewhere in between here. That's why in correctly classified point, you will be at this point. So correspondingly, you will get some loss. Whereas in this case, if you see, these points are inside the hyperplane, but the decision is wrong. Decision is wrong because it's on the other way around. So this will correspond to these points here. You will have this loss. Are you getting my point? So this is trying to show you the distribution of the data points in SVM and how this corresponds to the loss function that you have here. Okay. Any questions here? And this is again showing you same story, but now it is trying to show you how the L2 loss, which we were discussing last time, is problematic and why this particular loss is good. Because if you see here, this is again the loss function, L2 loss function, which is a parabola. Here you see for this correct decision boundary, you still have losses. Even if you are doing a correct decision, your loss is very high. Why it is like that? If you see the story of the data points which we have here, and I told you that if this point moves to this side, though it is a correctly classified point, but if it moves to this point, the loss will be large and your L2 boundary will change to this boundary, something like this. So similarly, here you can see it is because this point moved to this side, you have more loss. So this is showing you that even if the points are correctly classified, L2 loss is giving you some value which is not good. It should not give you any value. It should give you 0 value. That is given by this particular loss function which is here. But L2 is not giving you that facility. So this is showing you that. Okay. Okay, then this is the same story where I have written the loss function and lambda is equal to 1 by c. So the important point is if I make lambda equal to 0, that means c is infinity because lambda is equal to 1 by c. So if you make lambda equal to 0, then what will happen is this is the function. Obviously, if you make this term go to 0, it will be this function only, right? So now if you compare, this function with the perceptron loss function, then you can see the only difference is that this one was not there in case of perceptron. In case of your SVM, soft SVM, this is there. So this is the advantage of having soft SVM compared to perceptron, because actually you are getting this one and also you are getting this regularization automatically. See, I am keeping lambda equal to 0 just to show you how these two are equal. But if lambda is not equal to 0, you will be given some lambda regularization also. So this is the advantage that you get. Regularization also you are getting, and you are getting a margin of 1. So that is better as compared to the perceptron cost function which we had discussed last time. So this is the conclusion which you can see over here. That is the SVM soft L1 norm penalty with lambda equal to 0 is actually a perceptron in extreme situations. But in general, SVM allows regularization to be added to perceptron loss. So that regularization is automatically added into the perceptron loss, and that helps in regularizing the solution and giving the benefit of the margin. So this is the advantage of using SVM compared to your simple perceptron which we studied last time. So I hope the story you can link it out from very beginning to now to the SVM, like why we are going from a particular algorithm to the second one, to the third one, to the fourth one. So without motivation, or maybe say, if you just learn it, it's not wise. You should know why people have come up with these type of algorithms. So that has to always be in your mind, at the back of your mind. If you are reading anything new, you should first of all ask yourself as a question that why we are reading this, why it was not possible from the earlier algorithms. Then you will get a better picture of understanding these algorithms from different point of views. Okay. Okay, fine. So this is done. This is just testing. So if you want to test a particular sample, what you do is you already know this theta star. You already know this theta star because this is the solution that you are getting from the optimization framework lambda star. And then what you do is you just put them into this function, the boundary where you have signum function on theta transpose x plus theta 0. So here this theta star, I am putting this value which is given over here. So you can see now, this is just the substitutions only. So this is just substitution of the values, and then finally you can replace it by the kernel also, because you have transposed xi transpose xi. So basically this is the final testing. If you want to test whether the sample belongs to a particular class or not, you can do it through this. And the advantage of using SVM is that you do not have to sum up all the samples, because this lambda star is having some value for support vectors. For others it is all 0. So this is the thing. So this finishes off with your support vector machines. Next class we will study clustering algorithms, and I told you already that the last lecture will be already recorded, so you have to watch that. It's basically on hierarchical clustering, and today's class will be done by group number 10. Group 11 will be doing the Tuesday class, which we will do next time. Group 12 will be doing the recorded one, and if you have given me the group 13 permission and it's already there in classroom, then I will tell you what you have to do. So you have to prepare a separate note for some other topic. Okay. Any questions?